Hello and welcome once again to DT354, the design of reinforced concrete elements. Today we are moving on to look at our unit 3, which deals with the design of the reinforced concrete beams. Now, for us to go through our design, we are going to set ourselves another question. And our question says to design and detail the floor beam on the grid line D using the limit state design as outlined in the BS 8110, the part 1. Now, this will be the procedure for our design. One, we'll look at our preliminary sizing. We'll move ahead and do our estimation of our loads. We'll do an analysis of the moment and the shear. Check for adequacy for the preliminary sizes that we came out with. Design for moment reinforcement. Design for shear. Do a deflection check and a crack check. Now, this is the floor plan that we started with initially. And as the question says, we are supposed to design the beam on the grid line D. That is a beam that has been highlighted for us. If we move on to look at our structural grid that we came out with earlier on, for us to be able to design our beam, we are going to make use of the floor plan that we made use of earlier on in our unit 2 to design our floor slabs. And the question states to design the beam on grid line B. Grid line. And the question says to design the beam on grid line D. For our design data, we are using an exposure which is mild. The minimum grade of concrete that we are going to make use of is a C30. The nominal cover to reinforcement for durability is 25. That for fire resistance is 25. The minimum dimension is 20 mm. And for the grade of reinforcement, you are making use of the mild steel with a diameter of 20 mm. And the diameter of our length is also going to be 8 millimeters. Now, referring back to the structural grade that we came out with whilst we were doing the slab design, the grade line D has been highlighted in the green ink. So then that's the beam that we are going to design for this course or for this unit. Now, in order to design for our beam, the first thing that we'll have to decide for is our breadth. In order to design for our beam, the first thing that we need to determine is our flange width. And per the provisions of the BS code, there are two methods in determining the flange width. One is by using what is referred to as the actual flange width, and the second one is by adding the web width to LZ over 5. And the BS code stipulates that whichever gives the least value should be used as the flange width for the beam. Now, the actual flange width is by dividing the beams that borders the sides. The actual flange width is found by dividing the slab that borders the sides of the beam into two. So then, considering the slab that we are designing, considering the beam that we are designing for, it has two slabs on the side. That's the slab bounded by the grid line ED and the slab bounded by the grid line D and C. Considering the slab bounded by the grid line E and D, it has a span of 4,500, and the one between the grid line C and D also has a span of 1,600. So then if you are finding the actual flange width for our beam on grid line B, then the actual flange width would be half of the slab between the grid lines E and D and half of the slab between the grid line with C and D. Therefore, in finding our actual flange width, it becomes the 4,500 divided by 2 plus 1,600 divided by 2. That gives us 2,250 plus 800, which ultimately gives us an actual flange width of 3,050. Now, the alternative to finding the flange width is by adding the web width plus LZ over 5. Now, the LZ is said to be the span of the beam. Now, to begin designing our beam, we'll start with our initial dimension. And with our initial dimension, the first thing that we need to establish is the flange width of the beam. Now, according to the BS code, there are two methods in determining the flange width of the beam. One is by using the actual flange width, and the other method is by adding the web width to LZ over 5. Now, if you take the flange width or the actual flange width is half of the slabs that borders to the sides of the beam. So considering the slab that we are designing for, or the plan that we have that we are working with, Our beam on grade line D has two slabs to the side, one with a dimension of 4,500 and the other one with a dimension of 1,600. So then the actual flange width for our beam on grade line D would be half of the slab between the grade lines C and D and half of the slab between the grade lines D and C. So moving on to determine our initial flange width, to determine our actual flange width. The actual flange width therefore becomes 4,500 divided by 2 plus 1,600 divided by 2. This gives us 2,250 plus 800, which ultimately gives us 3,050. So then our actual flange width is 3,050. Now moving forward, we go on to use the other method to determine our flange width. And the other method states that the flange width is equal to our web width plus LZ over 5. Our web width plus LZ over 5. Now our web width is equals to 250. Our LZ value is 4,350 divided by 5. This gives us 250 plus 870, which ultimately gives a value of 1,120. Now, according to the BS code, whichever method is used, the one that gives the least value should be used as the flange width, in which case the 1,120 now becomes the flange width for our beam. Now, having established our flange width, we therefore go ahead and establish the ratio between the web width and the flange width. So we find our web width divided by our flange width. Our web width has a value of 250 and the flange width has a value of 1,120. Dividing the web width by the flange width gives us a value of 0.22. Now this 0.22 is less than 0.3, which we are going to use in determining our initial dimension. Now from the table that we use for our deflection check, or while we're doing the deflection check, the table that we used for our span to depth limits, in order for us to use the values within that table for a flanged beam, the ratio of our web width to our flange width is supposed to be less than 0.3. And from the calculations that we've just gone through, we realize that the ratio is 0.22, which is less than 0.3, meaning that we can rely on that table to find our initial dimensions. Now, since we have the ratio of our web width to flange width being less than 0.3, it means that we can go and read the values within that column. And also considering the fact that the beam that we are designing for is a continuous beam, when it comes to the type of support condition, we are supposed to go and read along the row for the continuous beam, meaning that if we take our span to depth ratio, our limiting value is going to be what? 20.8, as highlighted on our slide. Now, having identified our limiting value, we now move ahead to determine our initial dimension, bearing in mind that our nominal cover to reinforcement is 25 mm, the diameter of our reinforcement is 20 mm, and the diameter of our length is 8 mm. So then moving forward, our span to depth is supposed to be less than or equals to 20.8. Now, by inequality, it means that our D effective should be greater than or equal to our span divided by 20.8. The effective span of our beam, as we saw earlier on, was 4,350. Now, dividing the 4,350 by the 20.8 gives us an effective depth value of 209.13 millimeters. Now, having found the effective depth, we now move ahead to find the total depth of the beam. The total depth of the beam is given by adding the effective depth to the concrete cover to half of our bar diameter and our length diameter, since the effective depth is the distance from the topmost part of our beam to the center of our reinforcement. At this point, we know that our effective depth is 209.13. Our cover to reinforcement is 25. Our bar diameter, because it is 20 mm, half of it will be 10. And the diameter for our length, as we realized, was 8 mm. Adding everything together gives us an overall depth of 252.13. Now, the 252.13 is the minimum depth that we can have for our beam, given that we do not want to exceed our span to depth limit. Now, what this means is that I can either increase it or maintain it as it is. So then I move ahead, and instead of relying on the 252, we move ahead and assume a depth of what? 400. Since the 200 looks a little too shallow for a beam, so we move ahead and adopt a depth of 400 millimeters. Now, once a total depth of 400 millimeters has been assumed, it means that our D effective value would also change, since our concrete cover, our bar diameter, and our length diameter do not change. So we'll have to go back and determine the new effective depth that corresponds to an overall depth of 400 millimeters. So then our new effective depth becomes the overall depth minus our concrete cover plus half the bar diameter plus our length diameter, in which case we have 400 minus 25 plus 10 plus 8, giving us a D effective value of 357 millimeters. So then our effective depth for our beam moving forward is 357 millimeters. Now, having established our initial dimension, the next thing for us to do is to go ahead and estimate the load that the beam is supposed to carry. For our load estimation, as we did under the slab design, we'll estimate for our dead load as well as our live load. Considering our dead load, the elements that we'll consider, or the elements that would make up our dead load, would be the self-weight of the beam and every load that we had on the slab, which would be transferred onto the beam. So then after finding the weight of the beam, we go back to our slab design, and whatever load or weight was being carried by the slab will then be superimposed on the beam that we are designing. Now, in order to find our self-weight for our beam, we again make reference to the BS648, the section that gives us the densities for the various building material, and particularly the densities for reinforced concrete. As we saw before, or as we saw during the design of the slabs, our reinforced concrete or our concrete are normally prepared using granite aggregate, which is a natural aggregate. So in picking our density values, we'll go and pick the density values for what? For the natural aggregate. Now, having picked our density value for the natural aggregate, we now move ahead to use that density to determine the self-weight of the beam. And again, just as we did under the slab design, our self-weight is going to be given is found by multiplying our density by the volume by the acceleration due to gravity. Now, once I'm able to multiply my density by volume by acceleration due to gravity, it gives me the weight of the element I am designing for. So for our density, we just saw our density to be 2,307. When it comes to the volume of the beam, our beam has a cross-sectional dimension of 400 by 250. That is how come we have the 0.4 multiplied by 0.25, and the total length of the beam was 6.15, with our acceleration due to gravity being 9.8. Multiplying everything through gives us a self-weight of 13.904 kilonewtons. Now, when it comes to the design of beams, usually our load values are left in terms of load per span. The load value that we have now is a pointed load value. So we have to distribute this load equitably along the full length of the beam. So then we move ahead and take the 13.904 kilonewtons and divide it along or over the full length of the beam, which is the 6.15. So dividing the 13.904 by 6.15 gives us a load per span for the self-weight only as being 2.26 kilonewtons per meter. So then when we pick our load of the beam spread over the entire span, it has a value of 2.26 kilonewtons per meter. A similar method was gone through or had been applied in determining the self-weight of the slab or the load from the slab onto the beam. And for that one, it gives us a value of 11.05 kilonewtons per meter. Now, summing the two dead load values together gives us the total dead load for our beam, in which case our total dead load now becomes 13.31 kilonewtons per meter. Having finished with our dead loads, we now move on to determine our live loads. For our live loads, once again, we'll make reference to table 1 from the BS6399 as we did for the slab design. And during the slab design, we realized that our self-load had a value of 1.5 kilonewtons. So then we pick the 1.5 kilonewtons as our live load. Then we multiply it to the area of the floor slab which the beam has to resist. We pick that 1.5 kilonewtons per meter squared and we multiply it to the area of the floor slab that has to be carried by our beam. Now, if we go back to our structural grid and zooming into the side where we had our beam, so then if we go back to our structural grid, particularly zooming into the point where we had our beam was on our grid line D, and to the side of our grid line D, we had two slabs. The slab to one side had a dimension of 4,500 and the other side had a dimension of 1,600. Now, when it comes to the slabs to the sides of the beam, the slides are being carried by other beams on it. The slabs are being carried by other beams on its side. So then if we pick the slabs to the side, which or how much of that slab is being carried by our beam on grid line D. Now, for us to determine the side or the amount of slab that is being carried by our beam on grid line D, one, we should be able to tell whether the slab is a one-way slab or a two-way slab. When it comes to one-way slab, it is the beams that line the longer length of the slab or the panel that carries the weight of that slab. So then for all our one-way dimension slabs or our one-way panel, it is the beams that line the length of that particular panel that carries the load of the panel. If we take our panel or the panel that I just marked out, dividing the longer dimension by the shorter dimension would give us a value which is greater than 2, meaning that this panel is a one-way panel. Now, under such a scenario, the beams being highlighted by blue are the beams that are actually going to carry the loads of that panel. Since it's a one-way panel, the beam on the longer side of that panel would be the beam that would actually carry the weight of that panel. Again, for all the other panels that are left, when we divide the longer side by the shorter side, you'd realize that would have a value of either 2 or below, meaning that all of these panels are two-way panels. Now, for a two-way panel, the weight of the two-way panel is distributed equally on all the four sides or all the four beams that borders the sides of the panel. So to identify the amount of slab being carried by a particular beam, you start from one corner of the panel and draw a line at 45 degrees. So you draw 45-degree lines until all the lines intersect So then, as I explained earlier on, if you pick a particular panel, provided that panel is a one-way panel, the weight or the load on that one-way panel is carried or borne by the beams that line the longer sides of the panel. If it's a two-way slab, starting from one corner of the panel, you draw a line at an angle of 45 degrees. So then from all the corners of that panel, a line of 45 degrees is drawn until they all intersect at one point, or until they all intersect one another. At the end of the day, you'll come out with a series of geometries, which is made up of triangles and trapezoids. Now, based on the side that borders to the particular beam that is being designed for, we can estimate for the area of the slabs that a particular beam is supposed to carry. So for the example that we are looking at, the part of the slab shaded in blue are the areas of the slabs that are beam on grade line D is supposed to carry. So then we now move ahead and estimate for the areas that has been shaded in blue. Therefore, starting from the topmost right part of our beam and labeling the various areas as A1, A2, and A3, we can move ahead and calculate for the areas of the floor panel that our beam is supposed to carry. If we consider area A1 is a triangle, and that one is determined by multiplying half the base by the height. This gives us a base. So this gives us half multiplied by a base, which is 1800, and the height, which is equal to 800. Multiplying everything So now moving ahead to calculate for the areas of the various parts of the slab that the beam is supposed to carry. We now start with area A. Area A has a trapezoidal shape. And so in calculating for the area, our formula becomes half A plus B multiplied by H. This is equal to half of A plus B is equals to 1.8 plus 0.2 multiplied by a height which is equal to 0.8. This gives us a total area of 0.8 meters squared. That is for our area 1. When we come to our area 2, our area 2 is rectangular in nature with a formula of D multiplied by H, where our breadth is equal to 4.35 multiplied by the height, which has a value of 0.8. Multiplying these two together gives us a value of 3.48 meters squared. And our last area is area 3, which is in the shape of a triangle with a formula of half DH, which gives us half multiplied by the base, which is 4.35, and a height value of 2.175. This gives us a total area of 4.72 meters squared. So then the total floor area being carried by the beam is equal to the area 1 plus area 2 plus area 3, which has a total value of 9 meters squared. So then the total floor area which is being carried by our beam on grid line D is equals to 9 meters squared. That is how come in finding our imposed load, we pick our imposed load value as we took from the BS6399, which is the 1.5 kilonewtons per meter squared. Then we multiply it by the area of the slab which is being carried by our beam. And since we are supposed to leave our loads in load per length, we divide everything by the total length of the beam, which is the 6.15, which ultimately gives us an imposed load value of 2.20 kilonewtons per meter. Now, having determined our total dead load and our total imposed load, we now move ahead and calculate for our design load, which is given by 1.4 multiplied by our dead load and our live load multiplied by 1.6. So we have 1.4 times 13.31 plus 1.6 multiplied by 2.2. This gives us 18.63 plus 3.25 with an ultimate design load of 21.88 kilonewtons. Now, having finished with that one, we now move ahead and do our moment and shear analysis, or move ahead and conduct our moment and shear analysis. This would help us determine the amount of moment and shear our beam would have to resist. The amount of moment and shear that our beam section would have to resist is calculated from a table in the BS code, that's the table 3.5, which gives us our moment coefficient that would multiply to our ultimate design load and our effective span to get the type of, or to get the magnitude of the moment within our beam section. Now, just to take you through the provisions of that table. Assuming we have this as our beam that we are designing for, the first column in the table talks about at outer support. Now, this makes reference to the ends of our beam. This makes reference to the ends of our beam. So labeling our support as A, B, C, D, and E. At outer support is making reference to the moment and the shear that would occur at the end support of our beam, in which case we are referring to our support A and our support B, or the moment that would occur at our support A and at our support B. At the second column, it talks about the near middle of end span. Now, the near middle of end span refers to the two end spans, or the spans at the end of our beam, in which case you are looking at the span between A and B and the span between what? D and E. So the near middle of end span is referring to the moment and the shear that will occur at the mid portions of our end span. So then that makes reference to the moment and the shear that will occur at the mid portions of our end span. Now, the next column talks about our first interior support. Now, the first interior support is the first support that we encounter once we move inwards from our outer support. The first support that we encounter that we move once we move inwards from our outer support. So starting from A, if I move inwards, the first support that I encounter is my support at B. So then that becomes my first interior support. From A inwards, my first interior support becomes my support at B, because that is the first support I encounter from the A side. Now, if I come and start from the other side, which is the E side, the first support that I'm going to encounter is my support at D. So then when the table talks about at first interior support coming from E, my first interior support becomes my support point at what? D. Now, moving from at the first interior support, we move to the at middle of interior spans. At middle of interior spans. Now, any span that is found in between the last two spans is being referred to as the interior span. So then we look at our span AB and our span DE as our end spans. Now, any span in between the span AB and the span DE becomes an interior span, in which case we would make reference to our span BC and what? Our span what? CD. So span BC and span CD becomes what? Our interior spans. So then at the middle of interior spans is making reference to the moment and the shears that would occur at the mid portions of our span BC and our span CD. And last but not the least is the at interior support, which is our last column. Now, this makes reference to any support that is located in between our first interior supports. Any other support located in between our first interior support is what is being referred to as the interior support. In our scenario, our interior support becomes what? Our support at point C. So then our support at point C becomes our what? Our interior support. So starting from A is an outer support, B is a first interior support, and C is an interior support. D is a first interior support, and our support E becomes what? Our outer support. So then having known what the various columns refer to, we'll now move ahead and apply it to determine the moment in our section. Now, if we take the beam that we are designing for, section wise, this is how our beam would look like. So then applying the provisions given in the table to determine our moment gives us the table that we have below, where for our moment at the outer support, it says that it has a value of what? 0. So multiplying 0 by our design loadings gives us what? 0. Now for our near middle of end span, our moment value is equals to